Hello. I'll give it just a few more minutes. All right, so the inverse square law, was one of the formulas that was slated for last week. Anyone remember what that equation was? All right, so it's I1 over I2 is equal to D2 over D1, and this entire side, this entire side is squared. All right, so when you and this is something that you'll probably see on the registry. It's not something that we do in real life, but of course you need to know it for testing purposes and you need to know it for registry purposes because you could potentially see it. So basically with radiation, the inverse square law, as the distance increases from the source, your dose, of course, decreases by a factor of 4. So the inverse square law is intensity 1 over intensity 2 is equal to the distance 2 over the distance 1, and both sides are squared. So let's see if I can make this bigger. This in the way. All right. So we have two equations here that we're going to work with. The first one, the radiographer standing at 6 feet from the IR receives 9 rem of exposure, and it wants to know how much he'll receive at 3 feet. 3 feet. So even if I didn't know how to work with this, common sense will tell me. So think of this like a campfire. If you were standing 6 feet away and you moved forward to 3 feet, should your exposure or the heat that you feel increase or decrease? Anybody?
You
Would
said
it
if you move
decrease?
further away,
You got closer.
oh, closer,
So
it
it
would
decreased.
increase.
All right, so you're standing at a campfire, you're standing 6 feet away from the campfire, and you move closer to it. Should the heat that you feel increase or decrease?
Oh,
Increase.
decrease.
All
Okay.
right. So same thing with X-ray, same thing with light. The closer you are to the source, the more light you are going to get, let's say on the pages of your book. The farther you're away from the source, the less light. Same thing with X-ray. The closer you are to that source of radiation, the more you're going to get, and the farther you are away, the less you're going to get. So we have to know how to plug in. So this is basically algebra. Um, you have to know how to plug in or read the equation. So the radiographer was standing 6 feet. 6 feet is the very first distance. So for me, I kind of try to decipher what uh where each number is going to go. So where's my pen? The pen go? Oh, there it goes. All right, so my 6 feet is my first distance. All right. At 6 feet, you receive 9 rem. All right, that is going to be my first exposure. I1. And then it wants to know how much um how much exposure. So your I2, that's going to be the question. How much exposure would you receive at 3 feet? So 3 feet is your D2. All right, so I plug those numbers into my equation. We'll work it out together and tell me what numbers you come up with. All right, I'm sorry. This is supposed to be 90 rem, 90 rem. Disregard that bar chart. I don't know why that came there. Uh, Okay. I have one answer so far. All right. So, a lot of students are saying that the answer is 360. Is there anyone that did not get 360? All right, we'll show the work anyways. So, 3 squared is 9. So I have 9, this should have been 90. 90 over x is equal to 9 over 36. We cross multiply here. 36 times 90 is equal to 3240. We need to isolate or get rid of this x, so 3240 divided by 9, and that gives us 360 rem. All right, so if we get closer to the fire, our dose increases by a factor of 4. All right, and 360 is basically 4 times that initial exposure. All right, the next one, go ahead and do that one for me. All right, this one, you were at 1 meter, and this should have been 4 milligray. 4 milligray air. And it wants to know what will be the dose if you move to 3 meters. So should your dose increase or decrease?
It should decrease.
Okay. It should decrease. Any answers yet? Mhm. Intensity at 1 meter. All right, I saw one answer. What was that answer again? 4 divided by 9. All right, is it 4 divided by 9 or 9 divided by 4? Okay. All right, so the answer is 0.444 milligrams of air. Milligrams in air. And it was, so we need to isolate the x, so it's 4 divided by 9, and that gives you that number right there. All right, so any questions on the inverse square law? If you got 2.25, you did 9 divided by 4, but it's actually 4 divided by 9. Now, did we plug the numbers incorrectly if you got 2 let me see if you plug the numbers incorrectly. 4 over x is equal to, oops, what was that second number? 1 over 9. No, you wouldn't have got, I'm sorry, 1 over 3. It's just still 9 over 4. So I think you just messed up on your math. You still, seems like you still put the numbers in the right place, because if not, that would have been 9 times 4 divided by 1. So looks like you just divided wrong or chose the wrong number to divide. All right, so any questions about the inverse square law? Again, it basically tells how much dose you're going to receive at whatever distance. If you get closer to the source than you initially were, then your dose is going to increase. If you get farther away from the source than you initially were, then your dose is going to decrease. So even if you mess up the math altogether, before you start, get an idea of where that number should go. Should the number be higher than the original dose, or should it be lower than the original dose? And if you know it's going to be either way, anything that is above or below that, then you can start eliminating at least some of those answer choices. All right, so any questions about the inverse square law? All right, so let's go ahead and do some math, mass equations. All right, so some of the mass, determining mass is just pretty simple. It's your MA times the number times the amount of time, so times seconds. Some of the problems could give you the time in milliseconds, and some could actually give you the time in seconds. If it is in milliseconds, that means you need to convert it to seconds before you can proceed with the question. So the first one, I need for you to determine the mass. All right, so your first one is MA is equal to 100, and time, what is going on? Whatever, I'll type it. Time is equal to 0.25 seconds. All right, the next one is gonna be MA is equal to 500. And the time is equal to 100 milliseconds. And the last one, MA is equal to, and time is equal to, all right, so tell me what the overall mass for all of these are. All right, anybody know how to go from milliseconds to seconds? I'm sorry. All right, do we have our three answers yet? All right, so the first answer is 100 times 0.25. It should be 25. All right, hopefully everyone got that one. The second one is 50 times 0.3, so that should be 15, I believe. 50 times 0.3. 15 mass. All right, we have to deal with this milliseconds first. So 100 divided by 1000. Or you can always move your decimal, make sure I got that right. 100 divided by 1000. Or you can move your decimal point 3 places, 1, 2, 3. All right, and that's 0.1. So 500 times 0.1 gives us 50, I believe. All right, so one of the things again that the lecture from last week, it talked about the reciprocity law. And the reciprocity law basically talked about as you change your no matter if you double the MA or cut it in half, double the seconds and cut it in half, or double the overall mass, you should still come up with kind of the same answer, right? So how could I double? So this first one, let me get rid of. Everybody good with me erasing this? Yes? Okay. All right, so the first one says, let me get an easier one to work with. So let's say my MA station was 100 and my mass, let's just go with, I want to get a nice number to work with. I'm sorry, my seconds is, or time is 2 seconds. All right, so my overall mass for this one, do that. Jeez, come on. All right, my overall mass for this would be what? Anybody? 100 MA station at 2 seconds. Overall mass would be what?
200?
200. So what are some ways that I can double that mass based on the reciprocity law? So doubling the mass means I need for that mass to be 400. What are some ways that we could do that?
You can square it,
Square which one?
the 200.
Okay, so I could just double the mass. Yes, I can just overall take that mass and double it. All right, is there any other ways that we can come up with 400 mass?
You can double the 100 MA.
All right, so 200 MA times 2 seconds gives you 400 mass. All right, and what is the last way that we can double that mass?
Double your
Anybody?
seconds.
You can double the time, so we can go to 4 seconds. All right, and that will all give us 400 mass. So the reciprocity law just basically says no matter what we do, we can double the time, we can double the seconds, or we can double the overall mass. We should still come up with the same overall mass. All right, the next equation that was in your homework or your studies from last week was the 15% rule. So the 15% rule, if we're trying to let's say change our technique, KVP typically helps us with dose or patient dose. The higher the KVP, the lower the patient dose. And the reason for that is the x-rays are more than likely going to be able to penetrate and get out of the patient versus being attenuated or absorbed in the patient. So we don't always like to mess with KVP. If you remember last week, it does have an effect on dose, but it also has an effect on image contrast as well. So that's not a factor that we would choose first. But in any case, if we're trying to change the KVP, we would change it by either increasing it or decreasing it by 15%. So increasing the KVP by 15% would have the same effect as doubling the mass, and decreasing the KVP by 15% would have the same effect as cutting the mass in half. So if you wanted to see a change, you could either increase the KVP by 15%, or you could double the mass, one or the other. And if you want it to go the other direction, meaning you need less exposure, you could cut the mass in half, or you could decrease the KVP by 15%. All right, so let's say, so with the 15% rule, let's see. Well, let's work with the mass and KVP. And I want to see I want to get more exposure. I want more density. I'll say more density or more density or darkness on the image. So that means I need to increase, either double the mass or increase the KVP. All right, so I want to see it in terms of the KVP. So my initial KVP is 70. If I wanted to increase the density or the darkness in my image, what would that new KVP be? Vice versa, if I wanted to decrease it, tell me what that KVP would be. All right, we want to do it for 70 both ways. And also let's do it for 80. Both ways. 75 and a nice neat number of 100. All right, so depending on how you want to do it, if you like shopping, you like a sale, you can do it that way, determine what 15% is of the original number, and you could subtract it or add it, depending on which way you need it to go. Or you could actually use these two numbers. All right, if you need to go up, you want it to increase, you'll multiply it by 1.15, 1.15. And if you want it to go down, you multiply it by 0.85. So this is saying like 115%, and this is, of course, minus 15%. So either way, I could say 70 times 1.5, I'm sorry, 70 times 0.15 and figure out what that number is, which is 10.5. And I can choose to do take that 10.5 either way. I can either add it to if I need to see an increase, or I could subtract it if I needed to see a decrease. All right, so 70 plus 10.5 is 80.5. And 70 minus 10.5 is that 60? Wait, 60 point? No. 59.5. Let's see, 70 minus 10.5, 59.5. All right, so those are the new KVPs that I would employ there. Same thing, if I wanted to use that 1.15, 70 times 1.15 gives me 80.5, and 70 times 0.85 gives me 59.5. All right, so figure out the next three columns. What numbers would you have? All right, do we have our numbers yet? What is that? All right, the numbers that you should have we gotten all the way to the end yet? Oh, making me talk to myself. All right, so we'll start at the end, really simple. With the 100, 115% of 100 is 115, and the bottom one is 85. So you can either say 100 times 0.15, you'll figure out that's 15, and you can add it to and then take it away, or you can simply multiply those numbers, 100 times 0.85 and 100 times 1.15. All right, for the 80s, 80 times 0.85, that gives you 68 kVp. And 80 times 1.15 gives you 92 kVp. All right, 15% of 80 is 12. All right, so we simply added 12 or we reduced it by 12. All right, the last one is 75. 75 times 0.15 gives us 11.25. All right, and we can take it away or add it. So 75 times 1.15 if we're doing it the other way. 86.25. And the other one is 75 times 0.85. 63.75. So about 63 kVp and 86 kVp. All right, did anyone get anything different? Hold on. 75 times, okay. Why is that different? 75. Oh, 2 times, okay. All right, so that is how we either increase or decrease our KVP by 15%. So working with the 15% rule. All right, the other thing that I believe was introduced, am I good to erase this? Okay. All right, the other thing that I believe was introduced in last week's work was grid ratios. Where's the rest of my pages? All right, grid ratios and how we calculate grid ratios, the formula is H over D. All right, and the H is the height of the lead strip and the D is the distance between the lead strips. All right, so whenever we do get whatever that number is, it will be whatever that number is. So X to I guess a ratio of 1. So like 8 to 1 grid, 16 to 1 grid, 12 to 1 grid, etc. What you did learn or should have remembered from last week or learned from last week, the higher the grid ratio, the better that is of at cleaning up scatter. So a grid is something that we would use to clean up scatter. So you would want to kind of, if you had a choice of grids, you kind of want to weigh the risk versus the benefit of using that higher grid ratio. If you are employing a grid, so you're going from no grid to grid, your technique needs to increase. All right, the reason for that is those grids have the lead strips, and those lead strips are going to block any off-focus radiation, clean up the image, and clean up that contrast in the image. So 2 ways to clean up that scatter. The first way, if you remember from your studies, what's the very first way that we clean up scatter? Something that you should do every time you take an image. Anybody? All right, collimation. All right, collimation is the first way we're going to clean it up. And then the second way that we can clean up scatter is we can employ a grid. And we can't use a grid for anything, for everything. Times when you should consider using a grid is anything like a knee or larger, we would consider a grid. And a knee is kind of on the fence. You can do that tabletop or you can put it in the bucky. Anything bucky company does use a grid. It's called a Potter Bucky grid. You'll get into that later in your studies. But this is the mathematical equation for how we determine the grid ratio. All right, so I'm going to give you three pieces of information. All right, and it's going to be the height of the lead strip over the distance. So the first one is 1.6, and the distance is 0.2 millimeters. All right, what is that grid ratio? All right, the second one is 2.4 millimeters height, and the distance between the strips is 0.4 millimeters. And then the last one is 3.2 millimeters. And the distance between the strips is 0.2 millimeters. All right, what are these grid ratios? You just simply divide height over distance. All right, what are our three numbers?
8, 16. I mean 8, 6, and 16.
8, 6, and 16. All right, which one of these would be more efficient at cleaning up scatter?
Would it be 16?
It would be this 16-1. The higher the grid ratio, the better it is at cleaning up scatter. But the downside of this, or the disadvantage of choosing the one that's higher, a higher grid ratio, is we would need to increase our technique a lot more with this one. When I say increase the technique, the reason why we're increasing the technique is because the grids are going to block anything off focus. So when the x-rays reach or hit one of the lead strips, they're not going to be allowed to get through. So that means that what I overall initially had in my x-ray beam that would have all gotten to the patient, some of it's going to be blocked. So to counter that, I need to increase my mass so that I have more x-ray photons in that beam. All right, so if I'm increasing the grid ratio, either, let's say I'm going from no grid to a grid, or if I'm going from a lower grid ratio to a higher grid ratio, in either case, I'm going to increase the technique. If I'm going from a higher grid ratio to a lower grid ratio, or a higher grid ratio to no grid, then we would need to decrease our technique. All right, now the last thing that I believe it kind of discussed last week is the grid conversion factor. Let's see. Oh, actually, there was a mass, where's my pages? There was a mass distance equation. And then we have a grid conversion factor. All right, let's do the grid conversion factor first. Grid conversion factor. Grid. Eight. Other book, I'm looking for an equation. I'm sorry, a question. Revisit the internet. So here is an equation. All right, I'm going to go from no grid to an 8-to-1 grid. And my initial mass is 10. All right, the formula that you need to work with for this one is grid conversion factor 1 over grid conversion factor 2. And this is equal to mass 1 over mass 2. All right, what you have to put in your memory bank, we have a chart of the grid ratios. And basically with that grid ratio, there's a Bucky factor that goes with it. So your Bucky factor, so it goes, and this is something you have to put in your memory bank. So it goes no grid. And then we have 5, 8, 12, 16. Make sure. 5, 6, 8, 12, 16. All right, and the number that you would plug in for these is 1, 2, 3, 4, 5, and 6. All right, so here's the formula. I'm going from no grid. All right, so that is what I would plug in. Whatever no grid is what I would plug in for GCF1. So that is the number 1 to an 8-to-1 grid. All right, and an 8-to-1 grid is what number?
4.
4. All right, the initial mass was 10, and I want to know what the new mass is going to be. All right, so what should the new mass be so that I'm going from no grid to 8-to-1 grid? Should the mass increase or decrease? Anybody?
Should increase.
It should increase because I've added a grid. All right, so what would my new mass be?
Be 40.
40.
Correct. It would be 40. 10 times 4 is 40 divided by 1. That gives you 40 mass. All right, so let's do another one. Let's go from a, okay. Everybody good with me erase? Well, let me see if I could change the color. Everybody good with me erasing this? The left side? Okay. So let's go from a 12-to-1 grid to a 6-to-1 grid. All right, common sense. Which way should my mass increase or decrease if I'm going from 12-to-1 to 6-to-1 grid?
Decrease.
Increase.
All right, decrease. My initial mass is 50. All right, what should my new mass be? Conversion. All right, any answers yet? All right, 12 to 1, what number do I put in for that one?
Five.
What number do I put in for 6 to 1?
3.
Three.
All right, and over here I have 50, and I want to know what x is. 5 times 3 is 15, so I think that's 150 divided by 5. Right? Where's my math off? Calculate. 50 times 3. 50 times 3 is 150 divided by 5, and we get what? 30. 30 mass. All right, the next one. Are we good to erase? All right, the next one, let's go from a twelve to 1 grid. Change it to an 8 to 1 grid. My initial mass is 40. And what should the new mass be? We're going from 12 to 1, from 12 to 1 to 8 to 1. So should the mass be higher or lower?
Lower.
Lower.
Okay, so let me know what you get. I had one more. Okay, I got one answer. What did I say? 12 to 8, 40 mass. Okay. Yep, that number looks good. So 12 to 1 is 5. 8 to 1 is 4. 40 x 4 times 4 is 16. So 160 divided by 5, I'm guessing that is 32. All right, 32 mass. All right, how about let's go from a 16 to 1. Did I do that one already? 16 to 1 grid to a 5 to 1 grid. And the original mass was 60. Should it increase or decrease? Mass distance conversion. Okay, I have an answer. Couple answers. Mass distance. All right, someone said the answer was 20. So 16 to 1 is 6, 5 to 1 is 2. 60 times 2 is 120. Divided by 6 is 20. 20 mass. All right, so do we have the gist of this? Again, things that you need to put in your memory bank are your formula and this chart as well. This chart will not be given to you on the registry, so you have to put it in your memory bank. All right, the first one is easy. No grid is always 1. I have some students that kind of try to do this. Half of 6 is 3, half of 8 is 4, and then they remember the 6 for the 16, and then they fill in the rest from there. So however you need to put that in your memory bank. All right, now the last one is your mass distance conversion. And what I want you all to do for me, you research and find me a who wants to find me a question from the internet. Mass distance conversion. The formula was, let's see. Mass 1 over mass 2 mass 1 over mass 2 is equal to SID 1 over SID 2, and this entire side was squared. All right, the difference between this one and your inverse square law, your questions for inverse square law, they're going to be asking about intensity, whereas your mass conversions are going to be asking about mass. The distance is still the same, except for one uses D, one uses SID, but in this one, it's not inverted. Remember on the inverse square law, you had the second distance first. With this one, we have the first distance over the second distance. So someone find me an equation and write it on the board. Mass. Anybody? Not sure why this book doesn't. Oh, here's one. No, no, it's not. Let me see. Okay. Oh, here's one. I got one. Um, so the old mass, I'm sorry, yeah. The old mass is 125. The new mass, oh no, I want to know my new mass. The new mass is X. The old SID is 56. And the new SID is 40. All right, what is the new mass? All right, anybody have an answer? Okay, I saw one answer. Okay, so 200,000 divided by 3136, that gives you 63.77. So we're talking about approximately 6364 mass. All right, the next one, let's see. SID. Time. All right, so let's say I'll just make one up. Let's say our old mass is 100. And our old SID is 40. Um, and the new SID is 72. All right, what do you get for your new mass? Let's see. 72 times. Anybody have an answer yet? Okay. All right, and last one for the day. Of course, I'll have to record this lecture. I know I forgot to post the one from last week, but I do have it. I'll post it tonight. I'll have to record this and post it. But the last problem, hmm, let's say the old mass is 200. Actually, no, we can stop there. So let's work out that last one. I saw someone give an answer. So it was 100 over X is equal to 40 over 72. 40 times 40 is 1600. 72 times 72 is 5184. Um, 5184 times 100 is that right? Is 518 400, and that is divided by 1600. And that gives you 324 mass as the new mass. All right, so any questions about how you find the how you calculate the grid ratio, how you work with the inverse square law, how you work with the mass distance compensation formula, how do you calculate mass and what the mass reciprocity law kind of tells us, and what else did we do? How you work with your grid conversion factors. Any questions about any of those? So if we had a quiz on all of these formulas next week, we would be good to go. No head nods. All right, so again, anybody still unsure? This is your time. No?
I don't
Yes?
think I'm unsure. It's just that I guess the more I do it, it'll become easier. Just getting used to the formulas, the different formulas.
Okay. Who was talking? Is that Mercedes? Who was talking?
Yeah, that was me,
Okay.
Mercedes.
So yes, you do have to memorize these formulas. Of course, the math one is easy. It's just a matter of ensuring that when you're trying to calculate the MA times the time, if it's not in seconds, you have to convert the milliseconds to seconds. Inverse square law. Um, In my opinion, it's easy. Just remember that the distance is flipped on that second side, whereas the mass conversion formula, the distance is not flipped. All right. And the only thing between the two, this one's talking about mass, and inverse square law is talking about intensity. And then here it's flipped. So it's D2 over D1 squared versus distance 1 over distance 2. Of course, the grid conversion factor, GCF 1 over GCF 2 is equal to mass 1 over mass 2. Just remembering that box, the box of numbers per the different type of grid. And then how do you find the grid ratio? That's just height of the strip over distance of the strip. So again, a lot of formulas that you have to commit to your memory bank, and they'll just keep coming once you get to classes like Rad Bio, just more formulas to memorize. When you go for your registry, they typically give you like a white erase board. And what I always tell students, when you get that white erase board, once they say you can start, you want to take it, dump all your formulas that you need to know on that board before you start your test. That way you're not hanging on to, it doesn't get confused in your mind. So that is it for today. We were supposed to go over medical imaging equipment. In my opinion, some of it was kind of a repeat of last week, with the exception of it goes a little bit deeper into like the modalities in terms of, what is MRI useful for? What is sonography useful for? What are DEXA scans, which is bone densitometry, used for? What CT used for? So pretty simple chapter. So I'll record that and get it up. It also talked about your Bucky. What is our Bucky? Anybody know what the Bucky is? Per the VMC, that's the thing that's either under the table or it's in the upright Bucky that holds our cassette or our DR plate. So pretty simple chapter, just talking a little bit about portable equipment versus, the fixed equipment, which kind of was a review of last week, and then the other modalities you can get into. And it talked about diagnostic yield, meaning why would a doctor choose this, or what is this particular modality better for, or better to image with this one or better to image with that one. So that is it. If you have anything for me, you can always email me. Make sure you get those images loaded. I will give you until tomorrow midnight to get those loaded. And that's it if you didn't get them loaded already. And again, it was the abdomen. It was your 2 wrists. No, was it wrists? No, 2 elbows, 2
Elbow and a
forearms,
forearm. It was an elbow and a forearm. Yeah, 2 elbows,
chest.
the lateral, and then yeah.
Yeah. All right. So a total of 2, 4, 6, 7 images. So elbow, forearm, chest, and abdomen. All right, see you next week.